Thank you, Dave, for inviting me here. And I know there's a lot of students in here, and thank you for coming. I know it's near the end of the term, and I hope this will be a fun talk for you guys, and I hope it's pretty interesting to you guys because it's a nice, simple project that's very easy to understand, I feel, and I have really enjoyed doing it. So, to start with, I like to just kind of give an overview and kind of talk to people about how things are changing. You know, we've all heard climate change and stuff like that, and talked about all the talk about climate change and loss of ice and glacier damage and stuff like that. And we've all heard that, but it's hard to really visualize what you're actually seeing. And this is a picture of Yanapacha Mountain in the Cordillera Blanca. It's 5,500 meters high. The photo area is from about 5,000 meters or so, so there's 500 meters of vertical here. We're at about the snow line. And the first time I went here was in 2010, before I started any of this research. And I was going there for a mountaineering course. And I was looking it up, and it's like, okay, this looks like a kind of challenging mountain. There's a few obstacles here, and then nice little ramp up to the summit here, pretty easy climb. Okay, last time I presented this, everyone laughed there. It was a different group. Anyway, okay, different type of audience. All right. You guys understand doing this? Okay. All right. So I planned on going down this, and this picture is actually from 2009, so before I went down there to climb. When I got there, this is what it looked like. So look at that to that. These major crevasses opened up. This is a lot more like what you've seen, Ruth. Just major crevasses opened up. This entire mountain is just crumbling. And you can see this ridge line is totally devastated compared to what it was. Nice, not too bad. And it's a completely different mountain. The entire mountain is just falling apart because of the warming temperatures here. And this photo is from the beginning of March this year. I have a student who's going up there once a month to do some sampling. We'll talk about all that sampling. And he took this photo in March, and there's a few things that I want to point out here. First, if you look at this area, this glacier, you notice it's really dark. That's what I'm going to be talking about. It's the light-absorbing particles that are on the glacier surface. The sun hits it, and there's less reflection from it, so that the energy from the sun is being absorbed by those particles, warming up the snow around and melting more ice and snow. Another thing I want to point out, look at this. This rock wasn't there. So I'm guessing that a little bit peeked out of the snow and then got warmed up by the sun, and then it just spread and really opened up. I'm really curious to see what this looks like in a few weeks or a few months when I go down there. And the other thing that's really interesting, I'll show you some data from later on. Usually, this is March. This is the height of the wet season. Usually, it snows at that altitude. This is an El Nino year, and according to my student Wilmer, the snow line has been around 5,300 meters. It has been raining down here, and that's causing the glaciers to go away pretty fast. And it's one thing I've learned with this project is it's really important to continue doing measurements because there is so much variability year after year, because this area usually with the clean, with the fresh snow, it's usually really, really clean snow. So here's where you usually begin, the title of my talk, Measurements and Impacts of Light-Absorbing Particles on Tropical Glaciers. As Ruth said, I'm from the National Center for Atmospheric Research. I usually study up there, the clouds, but with this research with the American Climate Science Program, I'm studying glaciers. So ACSP I'll refer to it as ACSP. Four of us here formed this nonprofit organization back in like 2012, and it's been slow to get all the certifications and stuff like that. But these are the four co-founders, our website, our motto. Essentially what I like to say is we're people who are outdoor enthusiasts who like to go out into the mountains who can't shut off our curiosity. or scientists who are just, we can't stop doing science because it's so interesting. That's kind of what we do. So, and these are my main collaborators on this light absorbing particles project. And of course we have some other, I went digging through one of our old old PowerPoints and found this picture from Ruth, and I think this is 2012, 12 or 13, yeah, that's 12 on Maparahu, I believe, and yeah, so Huxley's been there for a lot of this ride. So this is another organization that I'm working with. It's called PSAC, Pollution and Its Impacts on the South American Cryosphere. It's an international collaboration, mostly South Americans, some Central and North Americans, and some Europeans who are working with us as well. We're all interested in what's going on with the cryosphere glaciers in all of South America. And it's a pretty interesting group. It's a very diverse group to work with, policymakers, scientists, modelers, all different types of scientists, and a few measurements people like me. And I put this photo up there. This is Yanapacha, the same mountain as in the first 3 slides, from that year that I did the mountaineering course in 2010. I wanted to just point out, similar to that March photo, a lot of really dirty snow in here. And one thing I want to just kind of point out, this will come out a few times. What does 2010 and 2016, what do they have in common? El Nino. So I think there's some pretty serious issues with El Nino years. And I'll come back to that, just different airflow patterns and potentially temperatures as well. So I put an outline up here, but it's really just an excuse to show a cool picture. One of the things I really like about ACSP is we try to reach out to the local universities. And these are 2 students here who, as far as I know, they had never been on snow before from the local university in Cusco. And we do that a lot. We take students from the local universities, teach them about the science that we're doing, take them up onto the mountains, give them experiences that they haven't had before. And it's really cool because a lot of them get just a new perspective on them. They live in the shadow of these mountains and they've never been there. And this is just a really good way for them to get the opportunity to get there. And we've had a lot of students we have like 10 students who are working on their thesis with us. And it's just a lot of fun to get them motivated and stuff like this. So that's where we're going as far as the outline goes. So a little bit of background on tropical glaciers. Between the Tropic of Cancer and the Tropic of Capricorn, 70% of the glaciers in the world between those 2 tropic lines are in the country of Peru. In the 1970s, they did a big aerial survey to determine the aerial extent of the glaciers, and they found 2,150 square kilometers in Peru. Before the COPE Climate Change Conference in 2014, 1,299. 42.7% decrease was the official number. In 2015, they were saying 1,273 or something like that. And with the El Nino, I'm guessing there will be another pretty substantial drop this year. 2 recent publications stated that the temperature changes and precipitation changes that have been observed cannot fully account for the loss of glacial area. That was in the Cordillera Blanca and the Cordillera Vilcanota. Cordillera Blanca is where we've been doing studies for 6 years. Cordillera Vilcanota is near Cusco, where we've been for 3 years now, or this will be our 3rd year. So the working hypothesis is that increased levels of light-absorbing particles, black carbon and dust on the glaciers is potentially leading to potentially substantially increasing this glacier loss. Why do we care? We've all heard about if we lose the Arctic ice caps, especially in the North Pole, the ocean will absorb a lot more sunlight and therefore warm up, and you get a positive feedback and you get less ice because the ocean's warmer and stuff like that. That isn't important here. This is not a global climate issue. If we lose all the glaciers in the tropics, it's not going to affect the planetary albedo significantly enough to seriously affect the planet, the climate. But our main issue is water supply. These glaciers are the water source for a lot of people, 95 million people in South America, and Lima, Peru is the second largest desert city on the planet behind Cairo. About 10 million people. And next slide. Lima, Peru, 10 million people. The water supply, this glacier. That's it. That glacier melts, goes down the river, and every drop of it goes into the Lima water system. And they're already, at this point, in near crisis phase with their water supply. And what's the future? I think really bad. These mountains that the glaciers come off of, the top elevation of those mountains is lower than Yanapacha, the one I showed before. So it's very possible that these glaciers are totally disintegrating as well. The Instituto Nacional de Estudios de Glaciología y Ecosistemas Montañas it's a Peruvian scientific institute interested in glaciers. Was that okay? Their director has specifically asked me to go measure these glaciers, and I am going and measuring those glaciers this year to see if there's an impact from the pollution of Lima. It's only 100 kilometers from this glacier to Lima, and it's very possible that the pollution from Lima could easily be really contaminating these glaciers substantially, in which case they could potentially have a serious problem. But in some ways, it's kind of nice because their problem is in their hands. If they can clean up Lima some, then they'll have less light-absorbing particles here, possibly. So, that's one of the nice things. It's in the northern hemisphere. China's a big source for the entire northern hemisphere, and it's hard to stop China. But in the southern hemisphere, for the most part, it's more local sources. Initially, before any warming starts, this is the your typical wet season flow, your typical dry season flow. Initially, when the climate starts warming, you get an increased water flow. And so all seems good. And after a while, the area has reduced enough so that counteracts the increase in flow because of an increased melting rate. So eventually you peak out, and then you start falling off a cliff. When the glaciers are all gone, you're much lower. So there's always three questions associated with this. How long? What's the time? How low? How much does it decrease? And where are we now? Time frame for this glacier, probably 20 years. For typical glaciers in Peru, probably 50 years, something like that. Larger glacier expanses, probably 50 years between the start and when you start to realize that there's a significant problem. How low in the wet season water flow rates can be down, would potentially be down 20 or 30%. So, this isn't an area that's seriously affected by droughts. So it's but, dry season flow in some places, as much as 70 or 80% down from what they would have been. So, imagine that Silicon Glacier feeding Lima was completely gone. You'd only have potentially 20% of the water flow going to Lima. That could be really bad. And where are we now? Just past the peak, a few studies have showed. So imagine you're a politician and there's not a lot of science going on and you don't have a real good grasp of science. There hasn't been any research on this. And the glaciers are receding, but the water's higher than ever. What do we need to do about it? There's just not that knowledge there, and that's kind of one of the issues that we're running into there. But the people there are listening, so hopefully we'll get through to them. So, light-absorbing particles, that's what I'm measuring. What's the deal? So, two pictures of snow. We have clean snow, not much going on, and dirty snow with a few little black specks. So, light hits the snow, and these little black specks, it could be, very little mass, little bits of dust, little bits of black carbon, and the albedo, the amount of sunlight that's reflected, is 2% less. You might think 2%, that's not a whole lot, but it actually worked out to be quite a lot when it's day after day after day for the whole entire year. That 2% over an entire year adds up to a lot of snow being melted. So if we go back here, the black carbon and light-absorbing particles shortens the time frame for everything. So it just crunches it up. Okay. So what are the sources of black carbon? This is in a lot of South American countries, there are emission standards, but they're not well enforced. So you get vehicles putting out stuff like that. Industry, of course. Cook stoves was a big problem in Nepal and India, and they've cleaned that up a lot, and that's also a big issue in South America. Agricultural burning, which in this case got away and burned down the whole mountain. And forest fires in the Amazon basin, as well as, news to me, in Africa as well. Potentially that black carbon can get to the glaciers. So the American Climber Science Program, this is what we do. Anyone want to go climbing? This is Pisco Mountain in the Cordillera Blanca, and we sample 3 or 4 different places on the mountain, climb up the mountain at night, and when the snow conditions are better. And with Pisco, I'm not sure if you're familiar with Pisco sours, we always grab an extra sample from the summit for Pisco sours. We started this work pretty much all as volunteers, so there wasn't a lot of funding to buy equipment because it came out of our own pockets. So I needed to decide to do this project, and initially I just figured I just had to start over with how to do these measurements. So I borrowed from a few other techniques and improvised where necessary. And so basically all we do in the field is we collect bags of snow. Pretty simple. Don't get too much dirty in the snow, and just collect plastic bags of snow, bring it down, and back in camp or back in town, depending on where it's, if you can get all the way to town, you melt the snow and then push it through filters. And that's what's going on here. And this is what a filter looks like that has a fair amount of junk on it. So that's a combination of dust and black carbon. So not able to separate between the two at this point, but working on that. So this is, when I started looking at this, I realized that this title isn't exactly correct because I have so many people working with this technique now that this is like every 2 or 3 months. I have a kitchen table full of samples. This was after, I think, the 2013 expedition. There's 100 different samples from different places that we sampled in the Cordillera Blanca, and I'm probably now getting 50 or so samples every 3 or 4 months. I've got a shipment in the mail coming in a few days. And to give you an idea, the sampling technique that I essentially invented, I have one publication on it, and this is where I have samples now. The yellow stars are where we're doing long-term sampling every week or every month throughout the year, and the orange stars are just all the different locations where I have samples from. And so this technique is gaining popularity mainly because it's easy and it's cheap, and it produces good results. So grad students can afford all the equipment necessary, which was kind of one of my goals, because in South America there aren't a lot of funds for research gear, so if they can do it for real cheap, they can actually do it. The competing instruments cost like $250,000, and my technique is a lot less expensive. So I've recently rebuilt my instrument for analysis of the filters. Basically, you put the filter right here. These are blocks of plexiglass, and there's an infrared thermometer sensor right there, and it's controlled by a little computer board and takes care of absolutely everything. And this basically measures the temperature of the filter. What are we interested in? There's black particles in the snow that are warming up when they're exposed to sunlight. So we get the black particles, we put them on a filter, we expose them to a light, and we see how much it warms up. So it's a pretty much skip the middleman, don't worry about it, just go directly to what you're interested in. So this new instrument that I refer to it as version 6.0 because I've actually built 6 different versions of this instrument to perfect it. here's some examples from, you turn on the light and the temperature of the filter increases, and then you turn off the light and it stops and it drops. This is my old instrument, and you can see here there's about plus or minus half a degree from the average in the spread. And with my new instrument, these were some tests I just did a few weeks ago in Germany. It's plus or minus 0.03. I've looked at some filters where you cannot see that there's actually anything on the filter, and I can easily detect what's on it. So this technique is, it's actually, unfortunately for this study, it's a little bit more useful for atmospheric black carbon measurements than snow black carbon measurements, just because it does well when you only have small particles. It does really well when you only have small particles, and dust tends to be bigger. So, but I think there's still a lot we can learn from it. It's still definitely a good technique that's far less expensive than anything else. And one thing I was going to say, we get effective black carbon, not actual black carbon, because there's dust particles there as well as the black carbon. So what we're actually measuring is all the particles. If they were black carbon, how much black carbon would that be to absorb the same amount of energy? So that's one thing that it would be difficult to separate the dust from the black carbon, but there might be some ways to do that. So in the first 3 years in the Cordillera Blanca, we got this type of results. I broke the measurements down into the different valleys, different regions where we were doing our sampling, and the different years. And this is published in a publication in the cryosphere. And you can see in the more distant regions, it's around 5 or 6 nanograms per gram. So that's nanograms of black carbon per gram of water, or the amount of energy that many nanograms would absorb if it were all black carbon. And then in these locations, closer to Huaraz, the largest town in the area, the values are quite a bit higher. So my thought is that the city of Huaraz is really affecting these mountains and not doing too much down here. In fact, when I took some actual snow samples to a lab in Boulder to look at what's going on in here, the scientist there was saying, "You have brought me the most boring snow on the planet," because there was nothing in it. He said the black carbon levels were less than Antarctica. And Pisco, less than Antarctica. But this is a nice trend. They're pretty similar across the board here and pretty similar low across there. And as I said earlier, things change. So this was a big surprise to see this. And I went through all my pictures from previous expeditions trying to see if this was brand new or if this was, how unusual this was. And every year before 2015 looked like this, looked really clear. So this could be from Trujillo and Chimbote, or it could be just biomass burning from the Amazon basin being pushed that way due to different weather patterns. But I think El Nino, in that time, the ocean off of Peru was like 5 degrees Celsius warmer than average. So that's got to be doing something to the circulation patterns. Okay. So to get an idea of what's happened since 2013, I like to say that, as I said, things change. So here's the 2011 through 13 graph. And then if we put the 2014 results on, fairly consistent to the north, and then these three are quite a bit higher in 2014. Perhaps an initial start on the El Nino effect, I'm not sure. And so to look at 2015, we have to squish everything down a little bit. And this is what we saw in 2015. So to give you an idea, the typical values here in 3, 4, and 5, that's those are fairly typical values for North American wintertime snow. So that's kind of what you would expect in, probably not here. It'd be cleaner here because you got a lot of Pacific Ocean to clean it up. And then, but as you get across the US, it's around 20 or 30 are typical values. And so we went from seeing 20 or 30 to, on the average, seeing, I think it was 110, 120 or something like that. You can actually see that. That visibly the snow is looking darker. The fresh snow is looking darker when there's that much stuff in it. So on to, here's another way of showing how things have changed dramatically. Wilmer is my student who took those pictures, and Wilmer's an incredibly motivated guy. He lives in Juarez, and he goes to Yanapacha Glacier once a month, and he goes to Schmitt Glacier once a month and collects samples. Every month he's been doing it for 2.5 years. And a few times he's even gone up there, stashed his bike somewhere, and then ridden his bike back. He does downhill mountain bike racing as well. But he's been doing these measurements for a little over 2.5 years. And you might look at this and say, what kind of a scientist is this? He can't put a decent graph together. Look at all these values from the first year. So, and as I pointed out initially with that photo from March, our first March, I think the value was 4 this is at Schmitt, actually near Juarez. And then our second March, the value was 3 at Schmitt and 4 at Yanapacha. So those are really low values. And the filters are in the mail to figure out what's going on this March. I should get them in a few days, but I'm sure it's going to be something like a few hundred. So in the second year, this is what happened. So this doesn't seem too bad. The Schmitt values are fairly high, but it's not crazy. But last year after the dry season, it just shot up, and then we kept getting rain and not much snow at all. It cleaned up a little bit at Yanapacha, but Schmitt it didn't really. And then in January, we still really started getting a lot of precipitation, rain, and just really dirty stuff. And this is like 286, and I'm kind of expecting March and February and March to be quite a bit higher. And to be honest, some of these values might be low, and I'm working on my instrument to figure out how to calibrate it a little better. And I'm guessing once I do calibrate things, this will go up a bit higher. So what does this actually mean? In that first year of measurements, we were able to calculate that we had between 25 and 70 centimeters of loss of glacier depth per year, just because of the light absorbing particles. So ignore everything else. The energy being absorbed by the light absorbing particles, how much snow would that actually melt? When I started working on that, it turned out to be a surprisingly easy calculation. But only 25 centimeters at Yanapacha, the cleaner area, and 70 centimeters at Schmitt, the more dirty area. I'm expecting this year that we'll be seeing values more like 1.5 meters to 2 meters loss because of the light absorbing particles, and that's substantial. There's there have been a few different studies where they've looked at total mass loss, total glacier loss, for everything without specifically looking at light absorbing particles, and it's around 3 to 5 meters in that area. So this year anyway could potentially account for 1/3 to half of the melting, whereas the climate change, temperature changes account for the rest of it. So that's why I'm pretty concerned about this. I really want to figure out what's going on that glacier that feeds Lima, because if we're losing glacier mass that fast or faster, and if it's crumbling like that initial glacier, then there could be substantial issues in the I don't know, 10, 20 years, they could be in a really major crisis, if not sooner. So, conclusions. So, Robin, we have fun. This is on Vaia Narahu Summit. Robin carried a papaya to the summit. And she didn't carry a knife, so she's chopping it open with her ice axe. So I didn't really know it at the time, but it turns out that these measurements of light-absorbing particles were the first in South America. This program that we started was the first measurements in all of South America. There are more measurements now with the rest of the PSAC group, but those were pretty much the first. And as I said, we're getting more and more measurements these days as more and more people become concerned about this problem. We've developed an easy, inexpensive technique to measure light-absorbing particles. The whole cost of all the equipment for doing the analysis of the filters, a couple $1,000 versus $250,000 for some of the other instrumentation possibilities. So this is something that local groups can do in different countries. It's something that's very affordable. You don't need the highest high-tech equipment to do it. One of the big concerns, and what I've alluded to with Lima, is that the glaciers near the cities appear to be the most affected. So that automatically suggests that the most important glaciers for your water supply are the ones that are the most affected. So even if all the glaciers are going away at a moderate rate, the most important ones for your water supply might be going away a lot faster. And we have numerous collaborations throughout Central and South America and Europe and Nepal and a few people going to Antarctica throughout the world who are working on these techniques. And I can't end a talk without listing all the people who have helped out with this research, all the volunteers who have helped out and collected snow samples and had a good time in Peru. And you're on there, Ruth. And, yeah. So that's it, Ruth. I kind of did in order from the first to the last. And I don't know why poor Wilmer ended up last, but but yeah, we've lots of collaborations with different groups throughout Peru and South America, and the Molina Center for Energy and the Environment has helped out with some funding for some of my travel, some of my research, and I've been grateful to them. They're kind of leading up the PSAC effort. And thank you very much, and I will take whatever questions you might have. I went too fast. So.
If I understood correctly, you said the temperature loss didn't explain all the loss in glaciers. Does this light absorbing, does this fill that gap or not?
We will see. It's a really tough calculation to figure out all the different aspects of it. Just figuring out how much actual mass is lost. The easiest measurement is to measure the glacier area and how much area is lost, but that doesn't necessarily directly correspond to the actual mass loss. And so there's a lot of uncertainty there, and if you're just using satellite data, there's still a fair amount of uncertainty. This could potentially account for a lot of it. One thing that in the past on Vaia Narahu Mountain, there's an area where there's this big wall, and every so often there's some really dark black lines. And I argued that was every year. And John argued that was volcanic eruptions. And I think we're both wrong now. I think that might be El Nino years. And trying to balance out all that and understand all that, and because this year I think there'll be a heck of a lot more loss due to the light absorbing particles than probably as much this year as there was in the previous 5 years, without El Nino. So I think it's a really hard one to really quantify everything exactly. And there aren't any places, as far as I know, there aren't any places in the world that have this type of measurement, monthly measurements. They do these measurements with ice cores sometimes to look at, what's going on throughout the year. but I don't think you can do as good of a job unless you're actually on the ground there and actually picking up snow. So this is, I think, going to be one of the better studies when we finally analyze all of Wilmer's data. And I'm really, it's kind of morbidly psyched that we got a clean year and a dirty year. So.
I know that other sites are just getting started with this, but have people made observations about drastic changes in the amount of black carbon on ice in other parts of the world?
There's a lot of the studies, and what I just alluded to, a lot of the studies really are more go to a place, take a measurement, a one-time measurement, and they don't really, there aren't many studies where they actually do long-term monitoring. So, it's kind of a bit of an open question. There are very few studies, you can, as I said, you can do it with ice cores, but there's a lot of variability. The black line that's the dry season, that's 5 different months. It's one black line. You don't know how much was there, each year. There have been a few studies where they've used ice cores and they can look back at the history and get an idea of what's going on, but very few. So, and definitely not in South America. So it's good to have a MOVID student who will go get a sample every month. So.
You talked a little bit about the contributing factors to the carbon in the ducts, but there's also mining that's going on. And so I thought it was interesting that some of the research that you're doing has helped lead the local governments to more regulations on how they maintain that dust. Do you want to speak to that?
I'm not sure how much I'm really not too convinced that mining is a huge source of dust. It's, to me it's a bit questionable. I know, a lot of the areas we see light absorbing particles a lot low down on the glacier and not too much higher up. It's really hard to say. It's hard to convince myself that dust from mines itself are really important. I've never looked over at a mine and seen just a huge dust cloud coming off of it. And you see dust from dirt roads. That's one of the I think that's one of the main sources of dust is just the dirt roads in the area. And what types of dust? That's one way to potentially get at is what types of dust are on the dirt roads versus what's at the mines versus the local dirt roads. I think that's just a hunch. That's probably a bigger contributing factor. As far as additional sources, there's some. I did a presentation down there, and afterwards, a local woman, asked me about tire burning, because has been a common practice to burn tires. It's illegal now, and apparently they just do it at night then. So all that, I don't know if you've. I was looking to calibrate my instrument the first time, and I wanted to order some black carbon powder, and black carbon powder is one of the main ingredients in tires. So, so it's automatically full of black carbon. They burn that, and obviously it's big black plumes. I couldn't get black carbon from their source. The smallest shipment would have been 2 tons. That was more than I wanted. So, yeah.
I was just wondering if this technique could be adapted to lower elevations where the precipitation falls as rain.
It's potentially. Yeah, there have been a few studies of black carbon in rainwater, and I'm actually working with one of the students that I'm working with in Cusco is really interested in that, so I gave him a specific type of filter that would be better for that size. Black carbon in the air tends to be smaller than when it gets in snow. In snow, the particles will coagulate when you get melt-free cycles, so the particles end up being a bit bigger. But in the airborne version, they're a bit smaller, and when they get washed out, swept out by raindrops, so it'll end up being smaller. So I suggested a different type of filter, but he hasn't been able to get clean enough measurements yet. So, but the city of Cusco, where I do a lot of measurements, city of Cusco has really, really bad air. Those of you who think about going to Cusco and checking out Machu Picchu, don't plan to do runs or anything like that in Cusco. Yeah. Yeah.
So since this is like some of the first measurements, how are the cities like Lima, who are like really dependent on like these glaciers as water sources, how are they like reacting to your findings, or are they yet?
It's a slow process, but that institute I mentioned, I'm not going to try to pronounce again. They're very concerned about it. That's directly the federal government. They're really interested in it. The Wilmer's working with that group, and he's gotten us a long ways with working with them. And so I think they're going to be paying attention. We've talked to a lot of local government officials in Juarez and stuff like that. And I think there will be people who will be listening, especially if I get over there to that glacier and find a lot of black carbon. I think that'll wake people up that there's, and whether or not they can do anything is a question. You can increase pollution controls, but with a city of 10 million people, it's really going to be hard to stop it. But what I say a lot when I'm down there, it's possible to control those emissions. We do it here. You do not have to reinvent the technology. The technology exists, you just have to get it there. It costs money, but not as much money as reinventing it. So, which is potentially the best hope for them. So, if it is a substantial source. So, typical scientist, hedging my bets.
Thanks very much.
Thank you all.